this is the situation that you will have. Okay, this is the situation. The robot, okay? You've all played around with this robot, okay? It can navigate and it can perform, various action with its hand, one hand. And there is camera attached to this thing. And there's also a lidar to tell you how far you are from the object, okay? And there's also a screen, okay? And there is also a remote control to teleoperate this thing, okay? You have this robot, and we're going to assume that in the cloud, so there's Wi-Fi link, whatever, and there is Gemini, okay? Or some LLM that you like, okay? You could actually have this Gemini embedded in this robot if you want. Okay, there is enough memory to download, a small LLM in this robot. Okay? Now, this robot, the operating system of this robot is called ROS. Okay? If you're PC, then you have Windows, OS, It's ROS here, ROS. Okay, it's ROS. And ROS has this nodes, and it's sending messages to other nodes, programs, okay? So we call that topic, right? And this program, there's a camera node, okay, that's taking pictures, and it's sending images to a program, okay? So there's, this will be the publisher, this will be the subscriber, image will be the topic, right? Because there's camera in here, and there's a camera node that's taking pictures, okay? And there is an action node, which is, a motor, various motors in this thing. There are 6 motors in this thing, right? 6. And this program can send action topic to this action node, okay? And that would allow this robot to take various actions, which I'll define, okay? So this is the situation with the robot, okay? So it's taking pictures. Why is it taking pictures? To define the state, okay? To define the state. Now, all of this is going to be sent to the LLM. The LLM is going to give you a list of actions to take. Okay, so the image is sent to Gemini, and you also give it the prompt. Some complex direction. Okay. I want you to make some coffee and bring it to John, and when he's done, bring back the cup and throw it in the trash can or put it in the sink. Okay, that's the task. And that will be sent to Gemini. And in order, the Gemini is going to give you a list of actions to take, and it's going to give it to the robot. Okay? Now, so this is the situation, and what needs to be done is, did I tell you everything? I told you about reinforcement learning, okay? Told you about the situation. What needs to be defined, or what one needs to be told? Can someone say something? The Gemini needs to know the capability of this robot. Huh? We have Jet Rover. It may be something else. The capability of this robot, what this can do, Gemini needs to know. Okay? So that needs to be defined, okay? And that needs to be defined in the following ways. So this is a situation. Everyone understand? This is the framework that you have, that you will be working with. Okay? So it's possible. You can be creative and have Gemini right in here. Okay? This you're communicating by Wi-Fi or some Bluetooth or whatever communication link. Okay? Maybe this is not what you want. Okay? Oops. So the robot has 6 motors. The motors are there. And you're going to define an action group. We call it action group. And in the action group, okay, so this is an example of pick center. Okay, we're going to define this pick center. And in the pick center, each motor is going to be given a value between 0 to 1,000. It's a value between 0 to 1,000, okay? And that would relate with the angle and various controlling the robot, okay? 0 to 1,000. And there is also time, duration, okay? So for 500 milliseconds, the motor 1, 2, 3, 4, 5 would be take positional value, whatever that's defined by 0 to 1,000, okay? And then the next 1,500, it's going to take a different positional value. And this whole sequence will be defined as pick center. Okay? This whole thing will be defined as pick center. And the details are, there is pulse width modulation that sets the angles based on these things. Okay? And this action group will be in the file pickcenter.d6a, and it will be in the robot. Okay? And you would have to define many of these things. And you can do that by, actually entering the numbers, okay, into the robot. Okay, and there's a manual to do this. Okay. Then, once these things are done, you need to tell the LLM the action groups. Okay? So here is what you have to define. So the action group, one action group will be turn right 90. That will be an action group. And how do you do, how is this defined? You turn it, so the action lists are turn, pick, place, and move, direction, left, right, center, and various values. And you take various combinations of action, direction, and the value, and this will be the action group. And you would have that file in the robot. You need to define this, and then you prompt the LLM. So this needs to be described in the LLM prior, and then what the LLM will do is you give a prompt, move the red cube to the center. So it's looking at the picture, image. It has this prompt, and it's going to give you the list of action groups to perform that task. You understand what I'm saying? Okay? Sequence of action groups the Gemini is going to produce. And then it needs to be doing this thing interactively, okay? Because every time you you do an action, perform an action group, what changes? The state changes. You have a new image. It takes the image and then it produces something else. Okay? So the whole situation in reinforcement learning framework can be viewed in this way. The real world, the camera nodes, the camera node will pick up the state. Okay, that's one. That state is defined, ST. And the robot will have a policy. Okay? You need to design your policy. What is a policy? It takes the state and produces what? This policy is just a function that takes the state and produces an action. And that action is what? That action is that maximizes the reward, long-term reward, okay? It picks the action that maximizes the reward. And this action is not exactly in terms of the motor angle, or it says, left, right, or whatever, and that needs to be converted into a statement that the motor understands. It moves, okay, so the robot moves, meaning it takes the action that the reinforcement learning tells you, and the state changes. Okay? Now, there are many ways to classify a reinforcement learning algorithm. There are essentially, I'm going to classify it in this way. There is an online reinforcement learning and there is an offline reinforcement learning. Okay? Online reinforcement learning is it's taking action and it's learning as it's going. The reward model is changing as it's moving in the real world. Okay, so this online trains policies by continuously iterating. So as it's moving, the policy changes as it's interacting with the real world. Offline is you gather data before you're actually running it. Okay? You have various robot interacting with the real world. You have your data. You take that data and you define your policy. And it's fixed. And you use that policy throughout. Okay? You will be doing offline reinforcement learning. So you need to gather data. Okay, you need to interact with the real world, the robot, teleoperating, and then you need to somehow define your reward function, and then based on that, you define your policy. Okay. Why would you, robots, autonomous driving, and healthcare use reinforcement learning algorithms. Okay, this is one situation. So for a certain situation, what action do you take? Driving, okay? If you're in some situation, as it's driving, which way would you go? Okay, what do you do? Do you brake? Do you push the accelerator? Go left, right? Healthcare, robot doing healthcare. Now, this situation, would you use online or offline? Online, you don't have a particular policy, okay? As you're interacting with the environment, you could do something bad, you could do something good. As you're doing it, you're setting your policy. What would you do, online or offline here? In this situation, you would never use an online. So online is experimenting. Okay, oh, this is good. This is bad. And then it's setting its policy. So autonomous driving, you would always use offline. You don't want to experiment. You don't want to explore. The word is explore some particular situation in it because it's dangerous. Also in healthcare. Okay. But places where you can make a lot of mistake, then you would use online. Okay. Generally, if you're really sophisticated, you do offline, and then as you're interacting with the real world, you do a little bit of online. Because each situation is a little bit different, and maybe your offline policy will not accommodate for real line different situations. Okay. So here is an example of pick up the blue cube. This is based on reinforcement learning and the robot that you have. Okay. So you're going to, in your project, you're going to be given sort of a maze, different zones, environment. You're going to be given cubes. You're going to give different objects. You're also going to recognize images. And what you're going to do is you're going to teller operate. Let's say you want to do some pick up the cube. You're going to teller operate and gather some data. You will be successful in some situations. You will be unsuccessful. But you will gather that data. That's data. And based on that data, you would come up with a good policy. So it's like supervised learning. Okay, since this is going into a lot of detail, but I think probably tomorrow. Oh no, next week. You'll be actually doing this. So there are a whole bunch of files that you need to have. So the first is in the robot, you have teller-operated data. Okay, collect that. Yeah, you have also, you want to save that. Okay, and put it in all that data into this storage space, this file, okay, which is in the robot. And then you take this into a server, your PC, and or Google Colab, okay, and you would train it using an algorithm called implicit Q learning, which is an RL algorithm, okay? And the model parameter of the IQL will be stored here, and you put that into the robot, okay? And you would run, you have also a code that would run this RL algorithm, okay? And it would give you the change in X, Y, and Z, okay? And it would move this robot, and it will also send back the new states, okay? The details of this will be presented by the TAs, okay? And here is an RL code, okay? You need to somehow load the library for the robot environment. You need to initialize it, and then you run your MDP algorithm. That's what is it called? Oh, God. 뭐였지? Markov decision process. Okay. Markov decision process is what I just said so far. It's the state, the reward and action, and what is it? The Q and the S, the Q and the V. Okay, that needs to be defined. Okay, so in the RL algorithm, the key is the reward. Okay, so you teleoperate, you store that data, and you have to define your reward function. Okay, so data set. So the data comes from your teleoperated experience. Okay, teleoperate this, and then sometimes you drop the cubes. You're going to be successful sometimes, you're going to be fail sometimes. All of that will be stored. Okay, and that will be the data. You're also going to be, given data. What is it? To teleoperation. In order to teleoperate, you need to code for this. In the what is it? The joystick. Okay, there's A, D, W, S, and O, and L. It gives you. It's already going to be predefined X, Y, Z coordinates, and also there's the pitch, yaw, and the roll. All of that will be defined in some way. It will be predefined for you. You may want to go and change it. Okay. So you collect your data, and we're going to give you code for this, a template code for this. And again, based on that data set, get reward. The whole objective is to define this policy. Okay, and policy is just a function that takes the state and produces the action. Okay, and what is the action that it does? It chooses. It tries to maximize the accumulated average reward. Okay, R stands for the reward. Okay, and gamma is discounted, meaning that the reward that you get today is more than the reward, the same reward that you collect the following day. Okay. And you would do this, once you have this, you would run this algorithm not in the robot, but in your PC or your server to get this. You get this, and then you put that into the robot. And here is an algorithm that will be defined by the TAs in more detail, okay, next week. It's a particular algorithm, offline reinforcement learning, okay? So that's it. I said everything, without going into too much detail. Next week, you will be doing this thing on your own, okay? And you'll be doing, investigating this algorithm, okay? Now, I just like to say that all of this lectures, the very short lectures, is geared towards your final project, okay? So today will be the last lecture And from now on, you'll be pretty much on your own, okay? We've given you, bits and pieces that will be required for performing the project, okay? And you can use our suggestion, or you could be on your own. You can use a different algorithm. You can use a different reinforcement learning algorithm. It's all up to you, okay? And also, many of the functions that the robot has hyperparameters or parameters that are predefined. You need to go and check those parameters, and you need to modify it for another environment that we're going to give you, okay? If you don't do that, you will fail in your project, okay? Okay, so that's, any questions? Okay, we're done, and good luck. So that's it, everything. ROS, SLAM, kinematics for robot, planning, and then AI, computer vision, a little bit of computer vision, a little bit of LLM, and RL, sorry. Okay, so you're going to use all of those to perform this task that we're going to give you. Last year, I don't know if you've heard about it, last year we gave you some environment, there's rooms, maybe 3 rooms with a picture in each of the rooms to define the room. So the room with the cat picture, room with the dog picture. And then we placed a cube. These cubes were colored cubes. And the task was to place the cubes in the appropriate rooms. Okay? So the robot is in a new environment, so it's going around using SLAM to understand where the rooms are, map out the whole environment. Then based on that map, it's given a complex task, put the cubes, in the room with the cat or something like that, or various things. And that was a task last year. This year, it will be a little bit more difficult. Okay, so you got to be ready for this. We're going to, stack up the cubes. Well, maybe we'll have also different, we only had cubes. Maybe it will be different objects, complex structured objects. And so you need to pick that up, appropriately. It will be fun. Okay, so that's it. If there's no questions, then we're done.